today the concepts that we're talking about are what's called numerical integration, and part of this revolves around the idea that there are some functions that if we try to find the area under the curve, we don't have integration techniques to evaluate it directly using definite integrals. So for instance, if I had the integral from, say, 0 to the square root of pi divided by 2 of the sine of x squared dx, and the x is squared, not the sine is squared, just the x is squared. If I have something like that, we don't have currently techniques to be able to evaluate that using direct, straightforward integration processes. Because if we tried our u substitution process, u would be x squared. The derivative of that is 2x dx. I don't have the x sitting out here I would need to take the integral of that. So we're kind of stuck. But for different reasons, we might have this thing show up. Now what I want to do is go back and go to one that we actually could do another way, but just illustrate to you what's going on. And that way we'll be able to compare the estimated values from numerical integration and the actual values we get from integration. So you can see there's some differences, but in some cases it's okay. We have to live with that little bit of error. So questions at the moment about this type of thing and the reason that we might need numerical integration? You may have a question about that? Does everybody understand that this cannot be done by techniques we already know?
Because it has to show up in the problem, right?
Yeah, the x has to already be here, and it's not here. We don't just introduce it. That's one of our challenges. There's two different techniques that we'll visit about. One of them is called trapezoid rule, which does relate to these areas of trapezoids that we did in Bellwork. The second one is called Simpson's rule, which is named after an individual that looked at them in a slightly different way. So we're going to briefly look at both of them. We're going to look at details on trapezoid and break it down. Simpson's rule is somewhat similar in a lot of ways, with a few variations. Here's the one we're going to use to help us work out numerical integration and trapezoid rule. I want to evaluate the integral from 0 to 2 of x squared dx. Right, now, can we agree that yes, we could do this by normal techniques? Yes, we could get a particular answer. Everybody realizes that? Right, I'm not doing this one because we can't do it. I'm doing this one because I think it's easier to find. What we want to do with this problem is I want to actually look at the graph of what this is going to look like. Yeah, something like that. And then this region is what we're trying to find the area for, is that correct? Okay. You guys are drawing. Give me a head nod helps. Do you agree? Okay. Here's the theoretical idea behind the trapezoid rule. It's similar to going back to what we did when we first started area under the curves. We will break this up into parts. And with these rules, we generally pick some multiple of 4. Not that that's really magical, other than we just tend to do that. We're going to start with n equals 4. Just have 4 separate divisions. So one of our tasks is going to be, if I divide this into 4 parts, what are my locations along here?
1. Or, oh, it'd be like 1/2.
That's a location. That's a 3/2 location, and I'm going to need 0. I'm going to need that left-hand endpoint. The difference between what we did before with rectangles and what we're doing now with these trapezoids is I still go up and I still find these values against the curve, but now instead of coming here and going horizontally across, producing a huge quantity of error, we can draw a diagonal line up here, we can draw a diagonal line up here, draw a diagonal line over here, and draw a diagonal line down there. It lessens the amount of error. We produce all these trapezoids. It still produces error, either more than or less than, depending on how it's drawn. but it lessens it, and that's why we use trapezoid rule. So now I've got this series of trapezoids next to each other, and I find the area of each one. Well, what's the area of a trapezoid again?
Height over 2 times a.
Yeah, sum of the bases and then times the height divided by 2. So first thing we want to do is we want to look at the height. How would I determine the height? Well, I mean, couldn't I find this distance all the way across the whole thing? And because I've got 4 of them, I could divide it by 4. So the way we're going to represent this height over 2 quantity in our trapezoid rule is we're going to take the endpoints, in this case b minus a, divided by 2, because of the 1/2, and then n being the number of divisions we create. Is that going to give me a height over 2 quantity for each one of those trapezoids?
So for this one, it would be 2 minus 0 divided by 2 times 4?
Yes.
Wait, B and A would, like the size?
Yeah, B and A happen to be these endpoints. And I'll have to write that out here in just a second. So what we would look at is, we might say that the area is approximately equal to the integral, b minus a over 2n times the integral from a to b. And then we're going to note that it's the function f of x dx. That's kind of where we're starting. And then the trapezoid rule says, oh, you know what, I'm mixing things up, I apologize. Please erase this. That's going to show up in just a minute. Sorry about that, everybody. That's what I want. I'm getting ready to do the b minus a. We're going to say that this area that we defined as a definite integral is now going to be b minus a, the height part, over 2n. And we're going to do it times. Now we have to get these base numbers put together. All right, everybody ready? I've tried to mess this up once or twice. So now what I need to do is I need to get these height values. So if I look at this first trapezoid, I need the function evaluated right here at this endpoint, and then plus this function evaluated right here at this endpoint of that little trapezoid. Is that correct?
Yeah.
And then I'm going to add to it this next trapezoid, which is the function evaluated at this endpoint again, plus the function evaluated at that endpoint. True? And then I move over and I have the function evaluated at that endpoint again, and the function evaluated at that endpoint. And then for the last one, I had the function evaluated at this endpoint a second time, and then the function evaluated at this last endpoint only once. Would you agree with that? And we're going to add those different things up.
Yeah.
So what we do is we assign this to be like x sub 0, x sub 1, x sub 2, and so on. There's x sub n. No. Yep. So when we work on here, we have f x sub 0, meaning that first endpoint, this left-hand most side. We use it one time. But the next endpoints in the middle, we use twice. Once here, and then once for this one. So they're doubled up. Then we add to it 2 times f x sub 2, and we keep going until we get to this area right here where we use this one twice. So fx n minus 1. But then the last one, how many times do we use it? So yeah, we just make that a one time. So it's 1 multiplies on either n value, but 2 times everything in between. Questions about that?
What's the n minus 1 thing?
What that designates is this one right before the last one. That's my last one, so that's the one right before. That's what that means.
So you're just, that's just there to indicate the end of the pattern?
Yes, it is.
Okay. So why would you include that? It seems kind of redundant.
For the most part, I would agree that it is. I do want to designate, though, how it begins, but then also, how do I get out of it? How do I end it? And I need to show you where the ending goes with the 2 multipliers and then the 1 multiplier. That's why I go ahead and put that extra step in there. I agree in general, if you look at it, you go, yeah, that kind of makes sense. Now, we're going to do our specific example here in a second.
Why do you have the x minus n, or x sub n minus 1 part?
Because I'm trying to designate with that notation this one right before the last one. That's a way to say I'm picking the one right before this. See, I designated that as x sub n. So one right before is x n minus 1. It just means that spot. I don't know how many of these n's I might have. I might have 150 of them. I'm not sure we want to do that, but I might have that many. So I need to be able to symbolize that with these formulas. Other good questions about this?